Hello students, welcome back to my class. In this video, I am going to discuss the solution of Schrödinger equation for a important potential called dark delta function potential. So let me first write what is dark delta function. So we know that dark delta function delta x has value 0 when x is not equal to 0 and it has a value only when x is 0. So this is the very narrow spike function. So this is a very narrow spike function. So this is a Dirac delta function delta x. This is x is equal to 0 and this is a negative axis. So this way we define delta function, and it is very useful function for theoretical physics. Now, delta function has the property also. This is if I take integrate delta x dx, its value comes out 1. That means from here I can say the unit of delta x is equal to 1 by length, 1 by L. So this is my delta function. But here I want to solve the Schrödinger equation for delta function potential well. That means I am going to take a potential Vx of type minus alpha delta x. So if I draw this one, if I draw my Vx, which will be equal to minus alpha delta x. So this is my potential well, delta function potential well. This is the positive x-axis. Now for this type of potential, I want to solve the Schrödinger equation. Now two situation arises. First case, when my energy is negative, my total energy is less than 0, and second case arises when my E energy of the particle is total energy particle is positive. So here delta function, you can see delta function has the value 0. It has value only at x is equal to 0. Other places it has a 0 value. And in my last video, we discussed the condition for the bound state and scattering state. So where I discussed, when I told whenever the total energy is less than potential at plus minus infinite, then the solution of Schrödinger equation will be bound state solution. Here v plus minus infinite is 0, because if you go x tends to infinite, then the potential is 0. When x tends to minus infinite, potential 0. Potential has the value only at x is equal to 0. So that means this is equal to 0. So that means E is less than 0. That means this type of energy will give you the bound state solution. And if E is greater than 0, so in this case, which is greater than both plus minus infinite, so this E greater than 0 will give you the scattering state solutions. So let me now solve. So today I'm going to solve the bound state solution. That means when my energy is E is less than 0 case. So let us solve. So we have a Schrödinger equation. We know what is Schrödinger equation. Schrödinger equation is del 2 psi upon del x square minus h cut square 2m plus Vx psi x is equal to E psi x. This is my time independent Schrödinger equation. And now I am going to solve this Schrödinger equations for 3 reasons. Okay, I say this is my negative axis. Okay, so left hand side of x0, I say this is my region 1, and I say this is my right hand side region region of x equal to 0 is region 3, and I say this is a very a narrow width from minus E to plus E, and this region I defined as a region 2nd. Okay, So I'm dividing this potential region in three parts: 1, 2, and 3. And for all the three things I'm going to write the Schrödinger equation. So let me write the Schrödinger equation for region 1. So say region 1. So in region 1, delta function is 0. So let me first write in terms of delta function, this equation in terms of delta function. So you have a minus h cut square 2m del 2 psi del x square. Now you have a alpha delta x psi e psi x. Now in region 1, delta function is 0 because it's a value only at x equal to 0. So my equation becomes simple: minus h cut square 2m del 2 psi upon del x square e psi x. And now this equation can be written as a del 2 psi upon del x square equal to minus 2 me upon h cut square psi x. So generally, this type of equation has the solution. This is like a simple harmonic motion equation. Use only solution like e power iota kx type solution. But here, because uh, e is negative, so I am defining my this constant. I am defining as a k square, k kappa square, which is equal to minus 2 me upon h cut square. So now, so this equation now, because I am defining small k equal to plus minus iota kappa. So now this equation has a solution of time. I'm writing region 1. So this equation will have a solution, say a e power kappa x plus b e power minus kx. So this is my solution for x less than 0 case. Now we have to again see only valid or acceptable solution, because at negative side x goes to minus infinite, and if x goes to minus infinite, this terms diverges. So we have to make b equal to 0 because this term cannot be present in the solution. So I can write that my psi 1 in region 1, psi 1 x is only equal to e power a k x, where k minus 2 me upon h cut square. This is my solution in region 1. Now, similarly, if I write for solution in region 3, so equation remains the same. Only now this is a solution region 1. If I write in region 3, so psi 3 also I can write same type of solution. Instead of this amplitude, I write c kx plus d e power minus kx. So when x greater than 0, region third. Now this is the positive x-axis. Here x can go to plus infinity. So plus infinity. So this term will diverges. So I have to put c is equal to 0. So that means in region third, or you can say as a positive axis, right of the x equal to 0. Psi plus, or you can write this is also psi minus x, because x goes minus side. So psi third will be now, this will be now equal to, this time c should be 0. So this will be equal to d e power minus k x. Now boundary value, the condition on the wave function is that wave function should be continuous at x is equal to 0. So if I make and these two should wave function should match at x is equal to 0. So if I put x is equal to 0 here, so this become a, similarly this become d, and they both should be equal. So if I keep both equal, then a should be equal to d. Okay, so a should be equal to d, because I'm writing that at x is equal to 0, psi 1 should equal to psi third at x is equal to 0. Both should match. So this become a equal to d. Now let me draw the wave function. So this wave function we have psi 1 region. I have a e power minus kx plus kx, and region second third I have the solution again a e power minus kappa x. We have a, in x greater than 0 we have negative, and x less than 0 we have a positive. So this is my solution, and if I draw this wave function, so this will be like e power x here, and this will be become 0 here, and both should will match here, continuity of wave function. So this is my psi x, and this is x equal x goes here in positive side 0. So this is the shape of wave function, and these two wave function can be combinedly written as a e power minus kappa mod x. So this is for x less than 0. This is x greater than 0. So if I write x less than 0, this will become x become minus mod x become minus x. So this become plus 1. And for x greater than 0, this is a mod x will remain positive x. So this will be the solution. So combined together, this solution can be written like this. Now, so we have put the condition of continuity of wave function, and we have reached here. Now we did one more condition. So we know the first derivative, generally the first derivative of the wave function also should be continuous. But that is true only for what? That is only true for piecewise continuous potentials. So here potential is not a continuous, it is a delta function infinite. So the first derivative of a function is discontinuous. Let us calculate the second condition. So we have the Schrödinger equation. We have a Schrödinger equation minus h cut square 2m del 2 psi upon del x square minus alpha delta x psi x, and then you have e psi x here. Now let us find the discontinuity into the first derivative of psi. So I integrate this equation from minus, as I told you here we have put the define a region, second region from minus e to plus e. So let us integrate this equation minus h cut square 2m minus e2 plus e. So if you integrate second derivative, we'll get the first derivative. Say dx minus alpha delta x psi x dx minus e to e, where e tends to 0, where this e tends to 0. And similarly here e minus e2 plus e psi x dx. Now if you carefully look this term here, this is the area of psi versus x curve. So suppose we have say some psi here, and I want to integrate the area at a point, because this is the same point, very close point. If I want to integrate, I want to find the area of this curve at x is equal to say some value. So this is the very same, this is almost same point. So here basically we don't have any area. So this terms automatically becomes 0, because psi, if you can say psi at plus e and psi at minus e are same. So this has a no width, and this area has a no width, so this is 0. So this area, so this terms become, right hand side term becomes 0. Now if I integrate this equation, so this equation gives me minus h cut square 2m, and if I integrate this one, so this gives me del psi upon del x at x is equal to plus e, at plus e, and this gives me del psi upon del x at x is equal to minus e, x is equal to minus e, minus e. This is the first term. And second term, we know the property of this delta function. So this is, because this is almost equal to e, x is here, x is equal to almost 0. So this will give me alpha at x is equal to 0. This function has a only value, other places it is a 0. So this function, this integration have value only psi 0. Psi 0 equals to 0. Alpha psi 0 equals to 0. So let us now solve this one. We know the values of the psi. So now this gives me minus h cut square 2m, and now this is region first, so I can write this as a del psi 1 upon del x at x is equal to 0. So e tends to 0. So I am moving this limit, e tends to 0. So this become at d psi upon dx at x is equal to 0, and this become del psi, this is the region 3, upon del x at x is equal to 0. And now this is equal to alpha psi 0. Just we have the function, just put the values here, and we'll solve this one. So let us now solve this one. So you have a minus, so you have a del psi 1 upon del x, del psi 1 upon del x at x tends to 0. So this will be a kappa. So this is psi plus minus, plus e was region third. This was region third, and this was region first, because minus e plus e is region first and third. So this I have to this one. So this will give you minus k e power minus kx at x is equal to 0. This become 1. So this has the value minus k. Similarly, we have the value of, this is my region first, and now this is plus e2 plus e means region third, and plus and minus e means this is the region 1. So this should be region 1. This should be positive. This should be positive. Okay, positive k. And now for del psi 3, del psi 3 upon del x, this will give you minus kappa a, x equal to 0. This value becomes 0. So let's put it value here. So I got this third, this will be minus kappa a, and this is the positive kappa a, and this will go here. So this become minus 2m upon h cut square, is alpha, and psi 0. So psi 0, if I put here, this should match. So psi 0 is basically equal to A. And now if I solve this one, this is a minus 2 kappa A is equal to minus 2m h cut square alpha A. So 2 cancel, minus minus cancel. So you have left with K value, kappa value is m alpha upon h cut square. And we know the uh, k square, k kappa square is equal to minus 2 me upon h cut square. So from here, I can write my energy, okay, del psi upon del x. So k will be here. So my energy will be what? My energy will be now here from here minus, so h cut square 2m k square, and k square value we have this one. So this will be h cut square k square 2m, and we will be having now minus h cut square 2m, kappa is m square alpha square upon h cut square. So this will be, so E will be minus m alpha square upon 2. So k will be k square. Let me check it here. How we defined k. So here k was minus 2 me, minus 2 me upon h cut square, and h cut square upon 2m psi here. So minus 2m upon h cut square here. This is here. This is correct. So now m alpha square, so k value is m alpha h cut square. So E will be what? E will be h cut square k square upon 2m. So E value will be here minus m alpha square upon 2 h cut square. This become h cut 4, correct? This become h cut 4. This become h cut 4. So this will be minus m alpha square upon 2. This is correct. Okay. I was getting confused. This is correct. So now here we have the energy value. So energy value is minus m alpha square upon 2h cut square. Okay, and kappa value, what is the kappa value? Kappa value was here, this is m alpha upon h cut square. Now let us write the wave function. So wave function will be now psi, I already told the wave function will be psi a e power minus kappa mod x here. So this will be equal to, so now we have a k value, and we need to now first normalize this function. So if I normalize this function from minus infinite to infinite, so this will be, normalization will give me normalization. So mod of a square minus infinite to infinite e power minus 2k mod x dx will be equal to 1 psi star psi minus infinite to infinite psi star psi dx is 1. Now this is the even function. So I can write this as a 2a square limit from 0 to infinite minus 2kx dx equals to 1. And if I solve this one, this will be, if I integrate this one, this will be 2a square This will give me e power minus 2kx, and this will be minus 2k, and the limit will be 0 to infinite equal to 1. So 2 cancels, and I have put limit here. So this is a mod of a square kappa. If I put 0 here, 1, infinite 0, so this is 1 equal to 1. So my a will be now 1 upon root kappa. This is my kappa value. So now I can write my wave function. So my wave function, we have only one wave function, root k. This will be root k, root kappa. It will be a will be root kappa. So root kappa is this one. So this is my wave function become m alpha under root upon h cut square. It will be h. It will be h, and e power minus kappa. Kappa is kappa kx. Root kx function is k mod x. So k is again root m alpha upon h cut mod x. This is my wave function. So see, it will be not root here, because here only kappa, we have only kappa here. So here root kappa. So here we have a kappa only, means this will be m alpha upon h cut square mod x. This is my wave function, and root of this one is here. And energy we have already calculated. Energy is we have seen the energy value minus m alpha square upon 2 h cut square. So that means delta function potential has only one bound state, only one function, and its energy is here. So there's only strictly a one bound state available for this potential. So in my next class, I will calculate the solution of Schrödinger equation for the same potential when my energy is greater than 0. That means for scattering state. So thank you very much. I'm stopping here.